Well, hello everyone, and we're here again with another Safer World by Design webinar. And today we have Bart van der Burg from Biodetection Systems, where he leads innovation. He's going to talk to us on the quantitative high-throughput safety evaluation of chemicals and chemical mixtures. I know you're muted right now, but during the talk and at the end of it, please make comments in the chat. If you'd like to join the discussion at the end, please submit questions to the question part of your screen, and we'll go through questions at the end of the talk, and then we can also have further discussion. If anyone wants to take the floor and share their thoughts, that'll be great. So with that, I hand you over to Bart. Over to you, Bart.
Okay, thank you very much, Barry. So good day. As Barry said, my name is Bart van der Burg, and I'll leave you now and shift to my presentation, because today I will introduce you to our methods for quantitative high-throughput safety evaluation of chemicals and chemical mixtures. Let's see how I shift. Yeah, sure. So chemicals are indispensable in modern daily life. Correct safety evaluation of chemicals is essential to protect humans and the environment. This should be done in the context of chemical mixtures to which we are typically exposed. Chemical safety issues in Europe are being dealt with in a harmonized way. The European Union has defined recently a Green Deal policy to come to a green, sustainable future. This ambition includes a zero pollution ambition for a toxic-free environment. The big question is how to reach this. Chemicals, typically humans are exposed to a complex mixture of both synthetic and natural chemicals. But only the tip of the iceberg is monitored and considered in risk assessment. Considering all chemicals in a mixture is not a trivial thing, since the basic principle of toxicology is that all chemicals are toxic, depending on the dose. Clearly, some of the natural, maybe green chemicals in the list are among the most toxic ones known to date. The champion is Botox, strangely enough, deliberately produced for cosmetics application. Clearly, removing all synthetic chemicals from the environment will not create a toxic-free environment. How to measure toxicity of mixtures then? Considering all chemicals that are around us. To measure toxicity of chemicals in mixtures, bioassays have been used throughout the time, and in fact are the only option. Traditionally, this has been done with experimental animals, which, depending on the application, range from simple bacterial systems like the Ames test to fish and rodents. The use of experimental animals in chemical safety evaluation is now under pressure, not only because of ethical reasons, but also because these tests are expensive, time-consuming, low in throughput, and often give unsatisfactory predictions of human toxicity. In vitro tests, giving a proxy of the processes in humans, are an attractive alternative. Therefore, we developed a range of CALUX human cell-based reporter gene assays. Cellular pathways that determine cell fate are the key interaction points of toxicants. A range of CALUX assays have been developed that quantitatively measure these key interactions. By measuring these interactions, CALUX assays can be used as alternative methods to assess safety of chemicals and chemical mixtures. This is how the CALUX assays work. It all starts with a chemical or a chemical mixture reaching the cell. It can then interact with a pathway that leads to a biological effect. An important target are receptors that act as transcription factors, activating endogenous genes leading to an altered biological effect. We have introduced synthetic genes in human cells that produce luciferase when the receptor is activated. When a substrate is added, a light signal is produced that is proportional to the amount of biological active chemical in a sample. In this way, sensitive, selective, and quantitative assays for major hormonal systems and cell signaling pathways have been developed. These address major types of toxicity. We automated these assays to reduce handling and increase throughput with very reproducible results. If needed, we can generate hundreds of dose response curves per day. And as you can see, these are very extensive dose response curves. We tested in this assay panel if you could reliably predict toxicity of chemicals as assessed in rodents. This slide shows a heat map of the assay outcomes for different compounds. All data points here represent an active score that increases in color intensity if the potency increases. Over 600 compounds were tested in different validation studies, and the results are encouraging, showing 75 to 100% accuracy. Endocrine disruption showed extremely promising results. Then let's focus on endocrine disruption, since this gives a good reflection of the approach we take. The US EPA has selected high-throughput screening models to predict estrogenicity, one of the elements of endocrine disruption, using 18 different assays for this single endpoint. Since it's not practical and not cost-effective to run all that many assays for a single endpoint, we compared their data with our very selective validated ER-alpha CALUX assay. The heat map at the right shows that our assay predicts reference data at least as good as the combined results of 18 assays. Moreover, since the CALUX lines itself have little metabolic capacity, we can improve predictivity by introducing metabolism in modular fashion, showing, for instance, shift with bisphenol A in potency if you add phase 1 and phase 2 enzymes. To further match with regulatory requirements, we successfully validated tests with extremely low variability of the results. This was the case within our own laboratory, but also between laboratories. We next asked the question, what would be needed for a full endocrine disruption panel that satisfies regulatory needs? The OECD has defined its testing framework, organizing tests according to increasing complexity and functionality. Level 2 of this framework lists all relevant mechanisms, which are interactions with estrogens, androgens, thyroid hormones, and steroidogenesis, abbreviated as EATS. A recent ECA-EFSA guidance document reinforced that choice. To be able to test these EATS endpoints in a regulatory context, we need a validated panel. For estrogens, androgens, and steroidogenesis endpoints, these are present, while many relevant tests are available for thyroid interference. We selected assays measuring 3 key endpoints in the thyroid axis, and a test guideline is also in preparation for this. As we have seen, in addition, metabolic steps can be introduced in the CALUX Biobased tests, further enhancing the relevance of this assay panel. Regulators have not been idle, and there are many relevant regulations to guide endocrine disruption testing. Unfortunately, so far no defined in vitro testing strategy has been defined, but EATS testing stands out as the most relevant endpoint anyway. Since in vitro tests often are relatively sensitive, industries are a bit hesitant to accept their results. Therefore, an important step to accept in vitro test results is to define thresholds of adversity to avoid false positives. These have been quite well defined for most tests, using reference compounds, normal background levels, which you can easily determine with our bioassay. But in this area, a consensus needs to be reached on these threshold levels. Also, in an early stage of design of a chemical, safety assessment is important. Safe design or green chemistry is an area in which the battery of CALUX tests is very promising, since it represents a comprehensive panel. Only a small sample of an experimental chemical is needed. It has a wide chemical application domain, for instance, being suitable for volatile compounds. It's highly standardized, rapid, and cost-effective. We used the CALUX panel successfully in the Resolve project to select novel non-toxic candidate solvents, and several publications are forthcoming in this area. An earlier study on novel bio-based phthalate alternatives that have many endocrine effects, focusing on avoiding these endocrine activity, has now been published. And what you can clearly see that furan dicarboxylic acid esters are extremely promising, having no activity at all. Recycling is one of the key elements in a green sustainable economy. Unfortunately, it's not without risks. One clear example which we recently encountered is that recycling of plastics containing brominated flame retardants can lead to the generation of brominated dioxins. We could clearly show that these compounds are as biologically active as the strictly regulated chlorinated dioxins. For instance, the brominated and the chlorinated congener have similar dose response curves here. Of concern is that they appear at extremely high levels, even in some children's toys. Then I come to some conclusions. So the CALUX high-throughput panel for safety assessment can be used for regulatory application, particularly read-across, safe design, and green chemistry. It is specially designed and very suitable for safety assessment of complex mixtures. Nowadays, we assess about 1,000 samples or 10,000 samples annually at Biodetection Systems, particularly focusing on these complex mixtures. Complementary chemical and biological methods, as well as the services of SaferWorldbyDesign and EU-ToxRisk partners, are available for even more comprehensive solutions. And you can think of any application you want. And with that, I come to the end of my presentation.